For many years now, I've been involved in environmental chemistry, trying to reduce the impact of chemicals on the environment. My name is Chris Rayner. I'm a director of C-Capture and I'm an academic from the University of Leeds. The issue we are tackling is anything to do with CO2 removal from various different gas streams, from biogas upgrading to power stations, but also things like natural gas upgrading and industrial carbon capture and storage. The way our technology works is you bubble your gas stream, usually containing CO2, through your solvent. The CO2 is held within that solvent and any other gases that are unreactive just pass through, so methane, nitrogen. You then pass your solvent into a desorber where it's heated up, CO2 comes off and you get your solvent regenerated, which you can reuse then in a continuous process. One of the problems with the current technologies is that it requires a lot of energy to actually separate the CO2 from the other gases.
All the energy you use to achieve that level of purity basically is a parasitic load. It's basically energy taken away from the bottom line, from your profits. My name is Casper Skolderman. I'm the senior engineer at C-Capture. If you take, for example, a landfill site, they take the methane out of the landfill site, they burn it and make electricity. And what you want for the customer is to use as little as possible of that electricity which they make for taking the CO2 out.
Our process reduces that amount of energy substantially by up to 90% when we're actually treating biogas. Biogas comes from anaerobic digestion and also landfill, and basically this is methane that also has a lot of CO2 in there. If you take the CO2 out, you can actually use the methane then in various different applications. It can go into the grid if it's refined enough.
Increase the pressure by compressing it and then you can put it into the gas pipeline. And another method is to liquefy it and then you can fuel, for example, trucks. So then it's a transport fuel. What
Current technologies for carbon capture and storage do, they tend to take the existing chemistry and then tweak the engineering. And that's pretty much optimized as much as it's going to be. What we've done is step back and change the chemistry as well, the underlying chemistry, and also then develop the engineering on top of that.
For me, the challenge is to keep the steel simple and cost effective. So any item that brings considerable cost with it, you want to optimize. So you don't want to oversize heat exchangers, you don't want to make tanks with too much wall thickness. So that's why we chemists and engineers work together again, is to keep the pressures low, keep the temperatures low, keep it all very nice and mild.
The long-term goal really is to get our technology implemented in very large-scale applications, particularly power stations, industrial sources of CO2 emissions. The sorts of savings on CO2 emissions that we can make are in the tens of thousands and millions of tonnes. It's an enormous potential. One of the problems we have as a population is the amount of CO2 we release into the atmosphere is enormous, and the only way to actually have a significant effect on that is large-scale implementation where you are capturing those sorts of amounts of CO2.